the Makemake. In this video, we're going to start by looking at the orbital period and Makemake's semi-major axis, as you can see, which is quite different from what we normally start with. We start with the aphelion and the perihelion, and then we find the semi-major axis and all that. But we're going to start by looking at the Kepler's third law, which states the squares of the orbital periods of planets are directly proportional to the cubes of the semi-major axis of their orbits. So the expression for Makemake's orbital period and Makemake's semi-major axis are, so as you can see, we have t squared over r cubed will be equal to 4 pi squared over gm. That's the equation for Kepler's law. But in this case, we're going to substitute with r with z. So it's now t squared over z cubed. Because z will represent our semi-major axis, as you saw in the previous videos for the planets that we looked at previously. So t squared will now be equal to 4 pi squared, and we have moved the denominator z cubed to the other side, so it becomes 4 pi squared times z cubed over gm, and then t will be equal to the square root of the constant multiplied by the square root of z cubed over gm, and that will be the answer. T squared is equal to 2 pi multiplied by the square root of that expression. And then we move on to the semi-major axis. We want to make z the subject of the formula. We do the same movements, but now we just switch things a bit. Instead of us doing it what we did by taking one variable straight to the next, to the other side of the equal sign, we invert the fractions. And after inverting the fractions, we then make z cubed the subject of formula, so we move t squared, the denominator, to the right side. Same thing what we did with z cubed on the other side when we're looking for the orbital period. So we're now left with z cubed is equal to t squared multiplied by gm over 4 pi squared, and then that gives us our final answer. When we move the cube to the other side, we get z is equal to the cube root of t squared multiplied by gm over 4 pi squared. So we know the orbital period for Makemake is 111,845 days, which is approximately 305 Earth years. So after 305 rotations around the sun for Earth, Makemake will be making its single orbit around the sun. As Earth is rotating 305 times, Makemake will be making its single orbit around the sun. It's very far from the sun, which makes sense. So we see the chain of conversions that's there, from into hours, into minutes, and into seconds. Multiply by 24 to get hours, multiply by 60 to get minutes, and then you multiply by 60 seconds to get those seconds, and we get the 9.660 times 10 to the power 9 seconds. Correct to it's 4 significant figures according to our calculation, but according to our normal rule, we put it to 3 significant figures because they are more accurate. So it will be 9.66 times 10 to the power 9 seconds, which is the orbital period in seconds. So the reason why we converted the period into seconds is because of the standard international unit of measurement for time, or the standard unit that's used in calculations, which is seconds for time. So when we then plug it into the expression that we derived for the calculation for the semi-major axis in the very first example, when we looked at the Kepler's law, we derived and saw that z would be equal to the cube root of gm times the period over 4 pi squared. So that's basically what we're doing. We see 9.663 times 10 to the power 9 squared will be the period, multiplied by 6.74 times 10 to the power negative 11, that's the gravitational constant, and then multiplied by the mass of the sun, which is 1.99 times 10 to the power of 30 over 4 pi squared, and then we cube root all of that, and then we get our answer as 6.797791403 times 10 to the power of 12, which is basically 6.798 terameters approximately. The tera is basically the prefix for 10 to the power of 12 meters. Then that's why I put terameters. And then 1 meter will be equal to 6.685 times 10 to the power negative 12 astronomical units. We want to convert those meters to astronomical units, so we multiply with that value for 1 meter in terms of astronomical units, and then our Z will then be approximately equal to 45.44 astronomical units, which is basically 45.4 astronomical units correct to 3 significant figures for accuracy. So for the next step, we're not going to cover the meaning of mu and theta. We have already covered that in the series video, in the Mars video, in the we are doing the Makemake, sorry, in the Pluto video. So you can revisit those videos and understand those two values, mu and theta, and what they represent in terms of aphelion and perihelion, and how we calculate the same major axis using those two values, which is basically the next step. Okay, for this next step is basically verification of the approximate value of the same major axis. So our same major axis, according to our definition, it is half of the longest diameter of an ellipse, and as we know, mu is the aphelion, which is the longest distance from the sun, and perihelion is the shortest distance, so it's more of like an average. But we see that in the calculation which says mu plus theta over 2 will be equal to the same major axis. So our aphelion will be 52.756, our perihelion will be 38.104 over 2, we then get 45.43 astronomical units, which is a difference of 0.01 astronomical units from our previous calculations. But when you put it to 3 significant figures, it's approximately 45.4 astronomical units, which is basically the same approximation that we used for our previous calculations. Usually use different methods to prove the same answer, so that you know that indeed you have gotten the right answer. If you use the same method in one trial, you're bound to get lost in the approximations. We're trying to make these answers precise and accurate, so you need to use many different methods. You can use the Kepler's law, or you can use this one of the aphelion and the perihelion. Basically, that's how you go about it. Before we go to the next part of the video, I think it's best if we realize that those brackets, the blue and yellow brackets, they're starting and ending from the middle part of the body, like the middle of the sun, that's where it's starting, and the middle of Makemake, that's where it's ending. I just want us to take note of that as we go on to the next part, because some people might get lost in the next part. We'll try and explain why those brackets are like that in the next part. It's basically the distance comes from the center of the planet to the center of the sun, or the center from the smaller mass to the center of the bigger mass. No, it doesn't end on their surfaces. So like we know from the previous videos that we've done, in 2006 the International Astronomical Union, the IAU, met and made some resolutions. One of them was called the resolution B5, which defined a planet, because there's different definitions of a planet, and we had many bodies considered as planets, but we needed to really define this word planet, so that we have specific features of a planet, or specific characteristics for that category of planets. And this is why we have the resolution B5. And then, because we had Pluto being one of the planets, resolution B6 was then created. I think we'll put a link in the description of this video, so that on the YouTube channel, so that you can visit the document, the soft copy of the document, which was published by the IAU. So you can see the definitions which changed Pluto from being a planet to becoming a dwarf planet, and likewise Makemake. So let us look at the note at the bottom left. According to resolution B5 of the Astronomical Union, the International Astronomical Union, a dwarf planet should have a nearly round shape, which is basically a perfect sphere, a Hence, it suffices for us to use the equation of a volume of a sphere to estimate the value of Makemake. Like we are going to see in the calculations, we already have a value of the diameter of Makemake and the radius of Makemake, which we can use in the calculation of the volume because of this resolution, or basically this assumption. Very common equation: volume of a sphere is equal to 4 over 3 pi r cubed. In some cases you can have negative 4 over 3 pi r cubed, but in this case we're not dealing with anything that needs a negative sign. We can discard it for now. So we just say 4 over 3 pi r cubed, and in our case, like I said, we already know what r is, which is the radius of Makemake. Therefore it will be 4 over 3 times pi times 715,000 meters cubed, and then we get that answer 1.531111,205 times 10 to the power of 18, and then kilometers is basically 1000 meters, so cubic kilometers will be equal to 1000 to the power of 3, and then that's why we have that value divided by 1000 cubed, which then gives us that value in cubic kilometers, and therefore the volume of Makemake is approximately equal to 1.53 times 10 to the power of 9 cubic kilometers, correct to 3 significant figures for accuracy. Okay, so this is the crucial part. We have a point mass experiencing a force of gravity on Makemake's surface. So we have that diagram before we look at the calculation. We have that diagram, and the blue dot that you see at the center of Makemake might not be exactly at the center. Everything is not to scale, by the way, so just try to visualize what I'm saying. So at the center of Makemake, which is where all the mass of Makemake is concentrated, to estimate the effect of gravity on the point mass which is on Makemake's surface. This is why you saw what I was saying on those brackets. The ends are basically directly at the center of the body, or at the center of the planet or the object. It's basically this blue dot which you're saying it's at the center. It's kind of saying we have all the mass of that object or that body or that planet at the center, because we're trying to make it a point mass where gravity is experienced, as we can see in one of the points stated here, which says the distance between the center where the mass is concentrated, the center of Makemake, and the white object on its surface, which is Makemake's radius. That's that green line. It's basically Makemake's radius. So we cannot find the distance between the surface of the planet and that white object. So we'd rather opt for the radius, which you all know, and we're trying to look at the greatest effect of gravity from right at the center of Makemake. And then we have the white dot there on the edge, on the left edge there, which is an object or a point mass experiencing the force of gravity on Makemake's surface. We're trying to get to the smallest particle. From there we can then build up to the greatest objects, but when you get to the smallest particle you can get the precise and accurate value of gravity than when you're dealing with bigger quantities and bigger objects. You might make some errors, but when you get to the smallest you get the real effect of this gravity. So that's basically how we look at it for the next calculation. By now you should realize that we're going to be looking at gravity, so hence we have this topic which says Makemake's surface gravity. So according to Newton's law of universal gravitation, every particle attracts every other particle in the universe with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. This is why when we looked at the the blue and the white dots, they were separated by the green line, which was the radius of Makemake. The blue represented one of the masses, which is the mass of Makemake, concentrated at the center, and then the white point mass was another mass, the other mass, and they're separated by the radius of Makemake. the distance from the surface of Makemake where the white object is experiencing a force, and the center of Makemake. So it's basically from the surface to the center of Makemake. That's where the radius covers, and that's basically the distance between those two masses that we're looking at just now. So according to the Newton's law of universal gravitation, our g will be the gravitational constant, m is the larger mass. In our case, it is the mass of Makemake, that blue dot, and then m is the mass of the object on Makemake's surface, which is that white dot that we saw in the diagram, and r is the separation of the masses. In this case, it is the radius of Makemake, the green line. Let us find g, which is the acceleration due to the Makemakean gravity. So according to the Newton's law of universal gravitation, the force is equal to the g, which is the gravitational constant, multiplied by the product of the masses, which is mass of Makemake and the mass of the object on the surface of Makemake, over the separation of the masses, which is the radius of Makemake squared. And that will be equal to, the reason why we are saying equal to mg is because force is equal to mass times acceleration, which is Newton's second law, that force is proportional to the acceleration of a mass. So we then see that F is equal to ma, but in this case this white object is experiencing gravity. That's why we're putting g. So the small letter g is for acceleration due to gravity, then the capital letter G is for the gravitational constant. Let's not confuse the two. So we're going to replace F with small letter m and small letter g. The small letter m is the mass of the object. So then say we cancel like terms, that's why you see m and m are being cancelled there. So we're now left with g is equal to capital letter G multiplied by the mass of Makemake over the radius of Makemake squared. And that's basically g, you already know it's 6.674 times 10 to the power negative 11 multiplied by the mass of Makemake, which is 3.1 times 10 to the power 21 kilograms over 715,000 meters squared. And then we get our g as 0.4047, which is approximately equal to 0.405 meters per second squared, to 3 significant figures. However, we have noticed something in our calculation right here, that we're getting a slightly different answer than some sources. So if there's anyone who has noticed any errors or any exclusions in our calculations, because we are trying to verify and proofreading and trying to use many other methods to verify what we've done, and we're still getting 0.4 meters per second squared, but we're seeing others are getting 0.5 meters per second squared, as you can see. So if you know why we are getting a different value, may you please put it in the comment section on the YouTube channel. As far as we're concerned, we are correct, because there are some sources that just leave it as below 0.5 meters per second squared. So that's why we think we are justified to make it 0.4 meters per second squared. So to help each other out, maybe you can assist in that regard and make our comment section livelier. But definitely, as you can see, I don't think we have violated any law. We have stated the law we used, we have stated how our variables are looking like, we have calculated for you. You can see the order of the calculation. So we really want to notice why people in other sources are mentioning 0.5 meters per second squared instead of 0.4 meters per second squared. That's something that we can help each other out, and we'll be looking forward to your suggestions or corrections in the comment section. As for our calculations segment, I think we're done. Enjoy the rest of the video as you learn more about the dwarf planet Makemake. Cheers. When is a Makemake?
like to be educated, but I'm so frustrated. Hello to my loneliness. I guess that ignorance is
around your Makemake.
to be for the new. Rewind, take it out of cue. Innocence can be a young man's game. Signed up for the hall of shame. I wish I knew how much I miss not knowing that we're all screwed when we play our roles and ignore the problems. I like to be weighing my patience. Stay up, I feel so outdated. How can we look the other way? Sun is out, but the sky is gray. What would happen if I took a chance? It's always hard at first glance. I don't wanna, but I know I gotta do it. The truth is hard to swallow, I think I'll chew it.